Alright, thanks for watching, and today we're gonna do something really cool, and something that's been bugging me my whole life essentially until I figured it out. Namely, I want to show you that in any dimension, the derivative of the volume of the ball gives you the surface area of the ball. So for example, in 2 dimensions, if you differentiate the area of a disk, which is pi r squared, then you get 2 pi r. So if you differentiate the area of the disk, you get the circumference of the disk. Or in 3 dimensions, if you differentiate 4/3 pi r cubed, you get 4 pi r squared. In other words, the derivative of the volume of the ball gives you the surface area of the ball. And I want to show you this is not a coincidence, it's actually true in any dimensions. And the cool thing also, I will do this without even calculating the volume of the ball of the surface area of the sphere. Because sure, you could calculate them separately, differentiate this, and see it's true, but you would kind of feel awful about yourself because it would take 2 hours to actually derive those formulas. But none of that junk today. Okay, how do we do this? Well, first of all, I guess step 1. How do you calculate the volume of an object? Well, the volume, well, I want to see triple integral in 3 dimensions or double integral in 2 dimensions. In general, it's an mth integral, but I'll just write it as a triple integral. Let's read the mth integral, where m is just a dimension. So in 3 dimensions it would be the ball, in 2 dimensions it would be a disk, of 1 of dx1 up to dxm. Again, in 3 dimensions, the volume of a ball is a triple integral of 1 over that ball. Where again, E is just a ball of radius r, right, capital R in Rm, so in m dimensions. M dimensions. Ball, if you want centered at 0, but it doesn't matter, any ball of radius r works. Okay, and first of all, what we want to do, we would like to change variables just because the radius turns out doesn't matter that much. You can assume the radius is 1 after some scaling. So let's first do a change of variables. So let's do u1 equals to x1 over r, u2 is x2 over r, dot dot dot, um is xm over r. And what happens, this change of variables, it turns the ball of radius r into the unit ball, namely a ball of radius 1. So again, if here you have E, which is the ball of radius r, if you apply u1 up to um to it, then you just get the ball of radius 1. So a smaller ball. So U turns E into E prime, where E prime is the ball of radius 1 in Rm. And that's because every side you've essentially divided by r, so in particular the radius becomes r over r, which is 1. Then the next thing is, of course, calculate the Jacobian. And the way I like to write this is simply as du1, du2 up to dum equals to, so I know there's some notation with partial derivatives. I hate that notation. I like just to think of it in terms of single variable calculus. To get du1 up to dum, that's du1 up to dum over dx1 up to dxm and dx1 up to dxm. And remember about the absolute value. So you can just think of a change of variables as just being a little cancellation, where you cancel out dx1 up to dxm, but you put the absolute values. And what is that? Well, it's just the Jacobian. It's the determinant of all the possible partial derivatives. So du1, dum up to dx1, dxm, that becomes just the determinant of partial du1 over partial dx1, partial du1 over partial dxm, partial dum over partial x1, partial um over partial xm. But here's the cool thing. So u1 only depends on x1. So you just get partial u1 over partial x1 is 1 over r. Everything else is 0. The second line, ux2 over ux1 over x1 is just 0. And then 1 over r, 0 up to 0. Lastly, 0, 0, 0 up to 1 over r. And the nice thing is you get a determinant of a diagonal matrix. So you just take the product of the diagonals. So 1 over r, 1 over r. And you do this m times. And you get 1 over r to the m. So in particular, d1 blah 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 equals to absolute value of 1 over r to the m, dx1 up to dxm. And this is positive, so you can just remove the absolute values. Good. So in particular, dx1 up to dxm is rm times the other one. So this is what we'll need. I know it's a lot of notation and not the most exciting part, but soon we'll get the exciting part. So dx1, what I'm saying is dx1 up to dxm is r to the m, du1 up to dum. So what do we have? The volume was again the mth integral of e of 1 dx1 up to dxm. But now, after a change of variables, what does that become? That becomes the triple integral over the unit ball of still the function 1. And what is this? Well, it just becomes rm du1 dum. This r to the m comes out, and we get rm, triple integral of the smaller thing, of 1 du1 up to dum. And what is the mth integral of 1 over e prime? That's just the volume of e prime. Rm of the volume of e prime. And that's the nice thing. E prime is just the ball of radius 1 in r to the m, so it's constant. It doesn't depend on r at all. And in particular, let's call that c. So that's c, r to the m. And what you get so far is that the volume is just one constant times r to the m. And that's one side of the story. In other words, what you're telling me, or what I'm telling you, is that the volume of a disk, or I guess the area of the disk, is something times r squared. So in fact, pi r squared. The volume of a ball in R3 is just something times r cubed. And in fact, 4/3 pi r cubed. In R4, it would be still a constant times R4, etc., etc. And the nice thing is, in this problem, we don't even care what that constant is. We don't have to calculate it to show that the derivative of volume is this surface area of the sphere. Because here comes the next part. On the one hand, we've shown that the volume scales at r to the m. But now let's find another way of calculating that volume in terms of the surface area. And this is where we need a theorem that relates an integral with maybe an integral over the surface area. So, step 2. On the other hand, well, V again was the volume of the ball. And that is the mth integral. Again, think if you want triple integral of 1 dx1 up to dxn. And what we would like to do, we would like to introduce some vector fields. So we would like to find some vector field f such that the divergence equals to 1. And here's what I mean. Again, this is E. Okay. And in particular, define the following vector field. So let f, now again, a vector field, I should put some boldface or arrow or something. So f of x1 up to xm to be 1 over m times x1 up to xm. Why do I do this? Because notice then the divergence of f, and again this just becomes x1 over m, xm over m. So what is the divergence? You take the first component, x1 over m, differentiate with respect to x1. The second one, differentiate with respect to x2. Up to the last one, you differentiate it with respect to xm. And what you get is just 1 over m plus 1 over m plus blah 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 plus 1 over m times. And if you do this m times, you get 1. And why was that important? Because the volume is the mth integral of 1, which becomes, in this case, reverse engineering, it's the mth integral of the divergence of f. And who says divergence? Says use the divergence theorem. So that becomes a triple integral over E of the divergence of f dx1 up to dxn. And the nice thing is the divergence theorem, and I prefer to call it the Gauss-Green theorem just because of Gauss, okay? It's a nice theorem that relates the integral of the divergence with the flux over the surface of E. So this then just becomes as follows. So that just equals to, again, that's by the divergence theorem. The double integral of over S of f dotted with ds, where S is the boundary of E, which becomes the sphere of radius r in Rn. So in other words, before we integrated over the ball, and now we want to calculate the flux of S of f over that sphere. So the sphere is just precisely the boundary of that ball. And well, how do we do that? There are two ways of calculating the surface integral. The annoying way is to parameterize your surface and to do f dotted with the f dotted with the sort of normal vector, or there's a much nicer way that's sort of parameter independent. That's the same thing as taking f and dotting it with the unit normal vector to your surface. And taking this quantity and integrating over S. So n equals to unit normal vector outward pointing unit normal vector of S at your point. In other words, at every point of S, you have a certain normal vector, unit normal vector n, and what you're doing, you're taking your vector field F, and at every point you dot it. Maybe something like that. At every point you dot it with your unit normal vector. And why is that useful? Because for the sphere, the unit normal vector is very easy to calculate. And let me derive what it is. So, I can't lift it anymore, but it's okay. Because, again, this is your sphere. And again, remember, everything has radius r. And suppose here you're at 0, and you're at the point x1 up to xm. On the one hand, well, you have the vector x1 up to xm. On the other hand, look at any normal vector. Suppose you have some normal vector, let's call it n hat. What do you notice? This vector, x1 up to xm, and any normal vector, well, they're sort of multiples of each other. So in particular, a normal vector would be x1 up to xm. And therefore, for the unit sphere, you just take this vector and divide it by a length. Because remember, for any vector, to get a unit vector, you just divide the vector by a length, by its length. So, what you get is that n hat is x1 up to xm. And so n is just the length of n hat over, n is n hat over the length of n hat, which becomes x1 up to xm over square root of, x1 squared plus dot 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 plus xm squared. But because, again, we're precisely on the unit sphere, we're not on the ball, because we're exactly on the sphere and not on the ball, this quantity on the bottom is precisely r. So x1, xm over r. And this will help us actually calculate that surface integral. Because what do we get? So we had double integral of f dotted with ds. By definition, that's just f dotted with n ds. And now look, f actually was precisely this. That was x1 up to xm over r, and you dot it with the same thing, x1 over xm over r. Okay. R? Okay. No, sorry. F was x1 up to xm over m. That's why. I was like, that doesn't quite make sense. So x1 dot 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 xm over m, you dot it with x1 dot 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 or xm over r ds. And what you get is, so this mr comes out, 1 over mr, double integral over s of x1 squared plus dot 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 plus xm squared ds. But again, because you're precisely on the surface of the sphere, this equals precisely to r squared. So you get r squared that comes out. So this then becomes r squared over mr, double integral over s of 1 ds. Lots of s's. But here's the upshot. If you double integrate the function 1 over some surface, it gives you the area of the surface. So here we get R over M of the area. So we get R over M times the area of S. But this is exactly what we want. We want the surface area. So what do we get in the end? What have we shown? So this is sort of the grand finale, step 3. So we have shown, okay, in step 1, we've shown that the volume is scales as R to the n times a constant. Okay. On the other hand, so we did that with a change of variables. On the other hand, in step 2, by using the divergence theorem, we've shown that the volume is precisely R over M times the area of S. In other words, so the volume is R over M times the surface area. So let's combine this to find the surface area. So we get R to the M times C equals to R over M times the area of S. So just solving for the area of S, we get then the following. Area of S is RMC M over R, which becomes, if you want, Cm R to the m minus 1. And so here's the upshot then. The volume is R to the MC. The area, surface area, becomes, if you want, M R to the m minus 1 times C. In particular, let's see what happens when you take the derivative of the volume. Volume prime is R to the MC prime. And again, C is the volume of the unit ball, which does not depend on R, so it's a constant. So you really get M R to the m minus 1 times C, and lo and behold, that is the surface area. So the derivative of the volume of the ball of radius R gives you the surface area of the sphere of radius R. And again, at no point did we calculate C, at no point did we calculate the volume of the ball or the surface area of the sphere. We've just shown that those two are related, which is already very neat, and the child in me can rest happily now. Alright, so if you like this divergence theorem extravaganza and you want to see more math, please make sure to subscribe to my channel. Thank you very much.